got me in.
Okay. Well, I have just started the recording. Thank you, everybody, so much for your patience. I really appreciate that. I wanted to start off with our sort of placeholder for land acknowledgement. We really want to think about how to transform land acknowledgements from conscience clearing rights to meaningful calls for action. We used to do them regularly before ABoVE meetings, but in May 2021, the American Anthropological Association had officially paused their land acknowledgements, and this was advocated for by the Association for Indigenous Anthropologists, and there was a task force that was created to investigate such gestures as part of a deeper inquiry to the historical relationships between anthropology and American Indian and Alaska Native nations. And I think that this is true for other disciplines besides anthropology and other indigenous groups as well. This task force has been impaneled. They were supposed to have guidance and a report or recommended actions in November 2022, but there hasn't been an update that I have been able to find. So we are still in a pause mode for this, but I did want to let you all know that that was where we were thinking about this. And secondly, I just want to quickly share my screen. So this is a part of our speaker series that is co-sponsored with the Government of the Northwest Territories Knowledge Agenda. And we have had, these are very occasional whenever people kind of volunteer to do this, or I can recruit some folks. And we have all of the prior recordings from other presentations are on our website. Once this is complete, there will be another one. I will let folks know that we have uploaded it once it's ready. If you are interested in presenting, we're always looking for new speakers. You don't have to be part of officially ABoVE. We're really interested in the work and interests of the broader community. So please do reach out to me. And if you got this because you were forwarded an invite and you want to continue to receive notifications about upcoming talks that we have, please do send me an email. I'll put that information in the chat so that you can contact me and you can get on our email distribution list. We have a similar one that is also focused on Yukon territory, and then we collaborate with a group in Alaska to do some Alaska-focused ones as well. So if you're interested in those geographical regions, also please feel to reach out to me. Now I'm going to ask Mike to, hopefully you should be able to share your screen and begin your presentation. And also if you could just give a brief introduction of yourself and where you're at. So I think Mike said he was going to talk for 20 to 30 minutes, and then we'll have some time for questions and discussion. If you want to wait and, raise your hand and, I mute people. Or also there is a chat function in WebEx in the lower corner. If something that comes out of your mind and you just want to get it written down, please feel free to use that as well. And we'll go through any written questions at the end at that time. So I am going to stop my video, and Mike, go ahead, try and share, and hopefully that will work.
Okay, thanks, Libby. Okay, let me know if
Okay,
you can see my
we
screen.
can see your screen. There we
Good
go.
stuff. And you got a full screen?
Yes, excellent. Okay, I'm going to mute myself. Go ahead and take it away. Thank you so much.
Okay, thank you, Libby. Yeah, I appreciate having the space here to talk about my work. So my name is Michael Merchant. I am a remote sensing scientist with Ducks Unlimited Canada. So it's a conservation organization operating Canada-wide. But I'm also a PhD student at the same time at the University of Guelph, which is also affiliated with the Canadian Center for Remote Sensing out of Ottawa. So I wear kind of both these hats. I'm going to be talking about 5 different projects that relate to these different positions. Most of them relate quite well, and in terms of those projects themselves, the topic of them will be remote sensing of wetlands across the Northwest Territories, and in particular using applications of Earth observation data and machine learning. So just a little outline. Okay, a little outline of what I'll be talking about. So I'm going to start off first with my Ducks Unlimited Canada work. So 2 projects in particular. One is modeling waterfowl abundance, particularly in the NASA ABoVE domain. So that is a NASA ABoVE affiliated project. And then also some of our operational wetland mapping work that we're doing across the Northwest Territories. For this project in particular, it's around the Clecho region in the NWT. And then following that, I'm going to talk a little bit about some of my ongoing PhD projects that'll be on large-scale wetland mapping using Google Earth Engine, polygonal ice band mapping with SAR and deep learning, and a final project on hydroecological mapping with interferometric SAR data. So, there we go. Okay. So first project I want to talk about is that NASA ABoVE affiliated project. So this work was on modeling waterfowl abundance in the NASA ABoVE domain. And this work was or is in partnership with Michigan Tech Research Institute. So we were working quite closely with them on different components of this project. But first for this project, I'll introduce a bit of the background of why it's important. First, with Arctic boreal zone wetlands, we know that they're quite essential for waterfowl species. For example, they provide refuge for drought-displaced waterfowl when the prairies are dry. And they're also important resources, or waterfowl are important resources, essential components of many Indigenous communities. So there's a good background here on the importance of both wetlands and waterfowl and how they connect to each other. And with our organization, DUC, we typically model waterfowl abundance using static wetland maps. However, a caveat is that the data that we often work with doesn't include temporal information on wetland characteristics. So with this ABoVE project that we've been working on with MTRI, what we hypothesize is that we could enhance our waterfowl abundance models or predictability if we included information on wetland inundation over time. So kind of what we refer to as time-varying inundation information. So with that, we had three key objectives that we've been working on with this ABoVE project. The first, which is to develop wetland type maps using Earth observation data machine learning methods. I'm going to be very brief on that and just showcase this because much of my presentation is on wetland mapping. So show the results of that first objective, which is, again, wetland type mapping for our key AOI, which is from the Peace Athabasca Delta, which is that red boundary there in that map, up to the Slave River Delta in the Northwest Territories, just along Great Slave Lake. So we were able to develop some wetland type maps of the AOI with our first objective. Second objective, though, was kind of this novel time-varying wetland inundation maps in a workflow that we've been working on. And three was to utilize what we've produced in 1 and 2 to develop these enhanced waterfowl abundance predictability models. So I'll start off with that second objective, which is the wetland inundation mapping. So this component of the project has been much led by our partners. So they were able to develop inundation maps of wetlands using Google Earth Engine and Sentinel-1 SAR imagery. And through the approaches they put together, they were able to detect inundation using essentially thresholding with SAR backscatter and also cross-pole ratios and an object-based approach within Earth Engine. And with the workflow that they put together, they were able to map Sentinel-1 scenes for 3 growing seasons. So we had identified 2018, 19, and 2020 for the time periods which we wanted to map our inundation conditions. And with these inundation maps, I'll show you what they look like. First, with each single SAR date or Sentinel-1 acquisition, they were able to produce these, first the image on the left, which is areas of open water, and then also areas of inundated vegetation. And with that information, we could summarize that into the map you see on the right, which is basically inundation extent. And then with this approach, they were able to produce what we call hydro period, which is just a summary of this inundation data over a given time period. So what that looks like with these multi-date conditions, you can see what those results look like for the 3 identified growing seasons, so 2018, 19, and 2020. And we have these nice maps of hydro period where we see inundation conditions over, in this example, the Peace Athabasca Delta. So once we had our wetland type maps and wetland inundation maps, we then wanted to acquire waterfowl survey data so we can develop and fit models for predicting waterfowl. And so that survey data, we were able to acquire it from the U.S. Fish and Wildlife Service waterfowl breeding population and habitat survey data. So I have a map here of where the extent is of that data across North America. So you can see the extent in yellow and also these flown transects, which is where the waterfall survey data is collected. And on the map there on the right, you can see some of the transects that are collected over the Peace Athabasca Delta, and then also the red area, which identifies our key corridor of interest. So for the waterfowl modeling itself, so what we did is we developed waterfowl models for two types of ducks. So that was diving and dabbling ducks. And what we first did is we developed what we're referring to as baseline models, where we really only use the time static wetland type maps. But following this, we then developed what we refer to as enhanced models. So those were utilizing both the wetland type maps, so the time static maps, but then also the inundation time varying maps. And really what I wanted to do was showcase the added value of inundation in this approach. And for the waterfowl modeling itself, we performed GAM modeling, which allows for nonlinear clustered responses between a dependent and independent variables. And GAM is an acronym for General Additive Mixed Modeling. So this is the workflow itself that we put together for assessing our different models. So we had a number of different predictor data sets from the type and inundation maps. We developed GAM models for both diver and dabbling ducks. But in particular from this workflow, just highlight in red here is what we were really trying to do was, again, assess the impact of adding inundation. So how much better can we predict waterfowl abundance when we have that novel time varying information in it? So some results here. So our models, what we did is we assessed them using a value called AIC, AKK Information Criterion. But just to be a brief and a little bit easier for this presentation, really it's just a method for evaluating model fit. And the lower the value, the better the model fit. So we can keep it simplistic like that for now. And I'll show you some results here. So on the left is our waterfowl modeling results for diving ducks in particular. So on the left is our very baseline model that only use wetland type data. And on the right is our enhanced model where you have inundation data added to the predictive model. Very simply, we can see that we have a lower AIC value indicating better predictive capabilities. And with our dabbling ducks, we're also finding a similar response in terms of the added inundation reduces or increases model fit. We get better results, better predictability. So very brief there on some of the results there, but we're seeing some nice added value with the inundation component of this project. And some visual results of these models. So what we were able to do is we were able to take these kind of best fit models and predict waterfowl abundance across our AOI, in particular the Peace Athabasca Delta. So what you're seeing here from this panel is the top rows are our best models predicting for diving ducks, and then the bottom rows are for dabbling ducks. And each column is a different time period for the prediction. So one's 2017, 18, and 19. And really what we're seeing from this project is that inundation can certainly improve waterfowl abundance predictability, which is quite important for organizations like ours, like Ducks Unlimited Canada, who's consistently looking to improve our ability to predict waterfowl abundance or map habitat suitability. So that was the first project that I want to talk about. It's our only ABoVE affiliated project, but I am going to get into some of our operational work at Ducks Unlimited Canada before we kind of head into some of the PhD work that I wanted to bring up. And first is a wetland mapping project across the Clecho region in the NWT. So this work is led by a colleague of mine, James Verghese, and he's working on mapping this quite large area, which is just northwest of Yellowknife. Use my cursor there to show where Yellowknife is for reference. So the background on the project itself is that our organization, DUC, has been working with the Clecho government in the NWT to map wetlands across the region. And we've engaged in this project by looking to essentially apply out our operational wetland mapping approaches to the region of interest to map the wetland types according to the Canadian Wetland Classification System. And again, our operational techniques, which I'll describe the workflow very briefly in a minute. Our workflow involves utilizing remotely sensed data, field data, and photo interpretation data to develop these wetland classification maps. So some objectives of this work. First, of course, to develop baseline wetland mapping of the region. We also would like to support land use planning in the region and Indigenous protected and considered areas, so IPCA. And really, just because this is a preliminary project, we're hoping to have it done by March. I'm going to talk about some of the preliminary reports and really just the baseline wetland mapping, because the land use planning and the IPCA development support that comes after the baseline mapping is done. So more to come there. But first, yeah, just want to introduce our organization's operational wetland mapping workflow. So I'll kind of walk you through this very briefly, but if you start from top to bottom, our workflow for mapping wetlands ingests optical, star, and topographic data. So it's a multi-source approach to wetland mapping. And those data sets, we ingest them into an object-based image analysis framework. So we often work within, for example, if anybody's worked with this software before, but eCognition software. And in order to work within the software and develop and train machine learning models, we have quite a large ingestion of photo interpretation data and fieldwork, which is very important to our wetland maps. But through the final steps of this, we run our data through a machine learning random forest approach to develop kind of a hierarchy of wetland maps depending on the need of the project. So kind of on the bottom row there, you'll see a wetland mask, a major wetland class map, and a wetland type map. So some of our projects differ in terms of their needs, but as a whole, our workflow is essentially what you see here for wetland mapping. Like I previously said, our operational wetland maps are quite dependent on accurate field data. So I'll show you some photos and examples of some of the field data that we had collected this past summer in the Clecho region. So you can see there's a high resolution optical image example, MS for multispectral, and some field photos of the different wetland types that we came across in this NWT region. First is a treed bog. Here you can see a pattern fen, a marsh system, a shrub swamp, so willow-dominated swamp, floating aquatic veg, so we often call it aquatic bed, and polygonal bogs were also prevalent in certain areas. So a lot of the kind of high latitude wetland types were obviously present across this area. So really beautiful landscape, really awesome field campaign we were able to complete this past summer. So I have a preliminary map of the region that my colleague was able to put together. We're hoping to have this final map ready by March. But in terms of the interim product, quite visibly, you can see that the area is very wetland and in particular peatland dominated, which makes sense at a high latitude region like the Clecho. But also it's a very burned area. A lot of fire scars you can see on this map within the red areas here. Anyway, so we are close to finishing this up and excited to see where it kind of takes the next steps of land use planning and IPCA development. So with that, I wanted to transition into some of my PhD projects that I'm working on, slowly getting across. In particular, many of them coincide with the Northwest Territories, so it's very fitting to this webinar series. So I'm going to start off with this first project, which was large scale Arctic wetland mapping within Google Earth Engine's cloud computing framework. So again, my PhD is affiliated with the University of Guelph and also the Canadian Centre for Remote Sensing through the Research Affiliate Program. But this project in particular had been working quite closely with Memorial University of Newfoundland. Dr. Masoud Madiampari has been helping me lead this project. So a lot of this develops off of the work that he's been doing for large-scale wetland mapping in Canada. So with this work, our objective really was to establish a machine learning cloud-based framework for large-scale Arctic wetland mapping. And so the study area itself was the Southern Arctic Ecozone, quite a large area that goes across Northwest Territories and as well as neighboring territories and provinces. You can see the kind of outline in teal there on that map. And much of it is within the continuous permafrost region and a lot of it beyond the tree line as well. For time's sake, I won't go into too much detail here, but you'll see that there's a number of yellow sampling plots that I've identified across this map here. So P1 to P10. So part of this work was actually looking to develop a pretty comprehensive reference data set repository which is really a need for large-scale machine learning methods. So just kind of showcasing where those sampling plots were and the process for deriving the sampling data necessary for this project utilized a number of different Earth observation data sets, which you can kind of see some examples there on that bottom row for each plot. Regardless, I'm going to jump straight into the methodology itself. So the entire process was developed within Google Earth Engine. So it's again a machine learning approach utilizing a number of different Earth observation data sets. For satellite imagery, that included Sentinel-2, 1, Alice Pulsar, but perhaps more importantly was some of the auxiliary data that was ingested into the methodology. So topographic data from the Arctic DM, hydrography data from Mirrored Hydro, and climate data from ERA5. And within this methodology that we've put together, we also tested both object and pixel-based approaches, which are really the two primary frameworks for classification with remote sensing. And I'll talk a little bit later about the implications of that and why we did it. But that was part of the workflow with this study in itself. And then to actually compare the object and pixel-based approaches, what we did is we performed what's called McNamara tests. So it's really just a chi-square of goodness fit, but the output is assessing for statistical difference between two classifications. And that's done by collapsing an error matrix from the two and looking for statistical difference. So I'll kind of show the results of that in a minute. But some of the first results or just observations within this work was one is that I put together what I'm calling a signature profile, which looked at the data responses from all the different sensors and electromagnetic points of the electromagnetic spectrum with the different wetland types. So you can see kind of this graph here, and what essentially this graph is showing is that wetlands really have unique signatures from different data sets and within different parts of the EM spectrum, which kind of paints the picture that multi-source Earth observation data is necessary for wetland mapping, especially at large scales as well. And then what you can see here is a figure showing the variable importance produced from a random forest algorithm, so within the algorithm that we're working with for this large-scale classification. And what you see on the y-axis is the different plots where I had sampling data for classification and assessment, and then the EO variables at the bottom. But what we're seeing here is, so with this variable importance, so darker reds indicate higher importance, but they relate quite well to the signature separability in the graph above. So basically where you see a nice signature separation in the plot above, you're seeing also good variable importance for the classification process itself. Regardless, though, it's quite different across the longitudinal and gradient. So again, it paints that picture of we need multi-source EO data for wetland mapping, especially over large areas where the landscape is quite different in different regions. So some statistical results of our different classification approaches. On the top is the object-based results, and on the bottom are the pixel-based results. And then on the right, you can see different metrics for the classifications that were put together. So metrics like overall accuracy, kappa, F1 scores, etc. And what you can see from the two approaches is that the accuracies themselves weren't very different. That's just visually looking at them. But if we put them through a McNamara test as well, where you have that collapsed error matrix, we're also finding that there is actually no statistical difference between the two, at least with these approaches. And that's at a 95% confidence interval. And the reason I went to these different frameworks is because there is implications for very large scale processing. So for example, with Google Earth Engine, if any of you ever worked in that platform before, you're often trying to develop efficient workflows. And if you're looking at something like in the case of the work I'm doing, something like circumpolar wetland mapping, you want to ensure that your machine learning approach is efficient, that you're avoiding computational inefficiencies or error timeouts, et cetera. So this kind of approach here, where we show relatively similar results that are not statistically different, it does, again, have implications on, for example, circumpolar mapping, which is a task that I'll probably be looking into over the next coming years with my PhD. So this is a good framework for how to get to, again, efficient, accurate wetland maps. And here's just a final image composite of the ecozone wetland classification. So the 5 different wetland classes were the focus of this project in my PhD. And on the left panel, you can see some examples there, some key regions. So the Tuktoyaktuk coastlands, the Queen Maud Gulf Bird Sanctuary, and the Harry Gibbons Bird Sanctuary. So yeah, depending on area, quite a high density of wetlands, especially peatlands and such as your fens and bogs. But with this map, I'll actually transition to the second study of my PhD that I wanted to talk about, because if you kind of focus on this top image of the Tuktoyaktuk coastlands in the Northwest Territories, you'll see from that map it's very bog dominated. So with that, I'll kind of transition in because the second study of my PhD was looking at mapping those bog features, which actually are ice wedge polygonal networks. So by the national definition within Canada for the Canadian Wetland Classification System, these ice wedge networks that are very prevalent on the Tuktoyaktuk coastlands are actually considered bogs. So with this study, what I was looking to do is I was trying to map those features by developing a deep learning convolutional neural network approach, which utilize candidate Earth observation data, in particular the recently launched RadarSat constellation mission data and Arctic DEM. Again, study area, Tuktoyaktuk coastlands, but just a bit of a background here in terms of trying to map these features. One of the reasons we looked at utilizing RCM is because it's quite a novel source of very high resolution compact pulsar data, which is kind of like the next generation of SAR data sets. However, with RCM in particular, it has been recently launched, so it is very little studied, especially for applications such as ice wedge mapping. So I'll jump quite quickly into some results here. So first, looking at some SAR scattering contributions. So you have a graph here showing the scattering contributions produced from an MCHI decomposition. For those of you that haven't worked with SAR data, what a decomposition does is it partitions the main scattering components for a different target based on different components. So with the MCHI decomposition, those components are surface scattering, double scattering, and volume scattering. And what you can see from this graph here is that the different target classes that we're looking at, open water, polygonal wetlands and uplands, or polygonal wetlands, which are ice wedge networks, each of them kind of display a very distinguishable scattering mechanism signature. If you look at that graph in D, you can see if you plot it in 3D, it is quite visibly different for the different classes that we're looking at. So it's a good sign for the efficacy of this platform for polygonal wetland mapping. But as I was showing in the previous slide, the workflow itself also ingested data from the Arctic DM into the CNN approach. So this is one of the variables we're looking at, which is the topographic wetness index. And we can see from these histogram graphs here, so you see a nice response in terms of wet pixels from different classes. So again, open water, polygonal wetlands, uplands. So there's a nice skew depending on the wetness of the classes. So another good sign for the CNN approach we've been putting together. And so just very general findings as we're wrapping up this study. With this work, I was able to develop an optimized CNN algorithm, which again uses RCM and Arctic DM as inputs. And very briefly, you have the architecture of the CNN below. And again, major finding, what we're essentially showing is that compact polarimetric SAR, which again, that next generation of SAR data sets, quite capable of accurately mapping permafrost features. And I have a little panel here of what those features kind of look like and some of the results. Top panel being high-res optical imagery, then an MCHI decomposition, so that those scattering contributions, some topographic data, the probabilities produced by the neural network, what those look like, and then a final classification map of the region. So some exciting work that I'm just starting to finish up, and hopefully over the next couple of months, we'll see some published work relative to this deep learning approach. And the final piece of my PhD that I wanted to showcase was a project that was looking at characterizing the hydroecological conditions of Arctic tundra ecosystems. So these classes that I've defined in this workflow, again being hydroecological, hydro being the state of wetness or dryness, and ecological being essentially the structural state of these classes. So is a system open, graminoid, or is it woody, such as trees and shrubs? So with this workflow itself, one of the main things I wanted to do was establish the value of interferometric SAR coherence, which we acquired from time series Sentinel-1. And the reason I was working with that is because there's been quite a bit of studies looking at the backscatter of SAR data for Arctic tundra mapping, but not very many looking at coherence. So what I did in this study is I looked at classifying SAR and INSAR data using machine learning methods, as well as due to the availability, we did include topographic data in this workflow as well. The study itself, though, was the Mackenzie Delta in the Northwest Territories, and the processing extent itself was the red excuse me, the red boundary you see here, which is the extent of a the Sentinel-1 time series data we were working with. And just a bit of a background just on coherence, which again was what I was looking at, really showing the value of in this study. So coherence, what it is it's the similarity of radar reflection between two SAR images taken at 2 points in time. So if you have your two SAR images and you're measuring coherence, if you have high levels of or high values of coherence, which range from 0 to 1, that means those 2 points in time are very alike. If you have low values closer to 0, it means those 2 points in time are very different. So we're going to hop very quick into some results here on some coherence observations. So what we see here is coherence measured over time. So we see some satellite image pairs and their dates on the bottom, and by class. And then also on the left graph, that's for the coal pole variables from the VV Sentinel-1 data, and on the right, the cross pole from the VH Sentinel-1 channel. And from these graphs, what we see first is that the coherence measured across this time period was much highest at the beginning of the growing season. I'm not going to dig too much into that, but really it was quite related to the environmental conditions at the time. So we have flooding, a lot of ice melt, etc., and a lot of rain in those first parts. So you have quite a wet landscape leading to a very consistent, actually, scattering mechanisms for certain classes. So that's what we were seeing there. But if we actually look at the different classes that are outlined here, so I shall just quickly walk through them, but the classes we were looking at were wet graminoids, so open wet systems, wet woody systems, so that would be kind of like wet shrubby systems, wet tree systems, but then dried woody, open water, tundra, and mountain unvegetated areas. But with those classes, what we're seeing is that open water and wet graminoid areas were showing basically consistently low coherence values across the entire time series. And with that, I'll kind of direct you to that image to the right, which is a false color high-res satellite image where I identified some wet graminoid areas with those yellow boundaries. And really, those are areas that are transitioning from open waters, and they're quite dynamic. You have water influencing them consistently. So it makes for an obvious observation that the coherence would be low from one date to the next. And then also surface water, you get a lot of impacts from wind and things like that. So typically open water is very incoherent from time to time. So that makes a lot of sense. But we have wet woody areas was the final class kind of looking at relative to, I guess you can say, wetlands. But they had actually much higher coherence from date to date. In particular, we kind of hypothesized that it's the consistent double bound scattering from wet ecosystems over time. But with this, I would just indicate that there are several distinct coherence signatures that you can see from these two graphs. And with that, it has implications for classification and trying to mapping these systems. Okay, and some final study findings here. What I was finding is that coherence variables are very complementary to SAR backscatter and topography. So again, with this approach, what I was doing is I was ingesting SAR backscatter, coherence, and topography into machine learning random forest classification approach. And what I'm showcasing here is actually the variables and the distribution of their minimal depth and mean in a random forest classifier. So for those who've worked with kind of random forest machine learning, we know that the variables used to make the first splits at the top nodes, they have the highest importance. So if we actually graph that by variable, you'll see that those with the lowest distribution of minimal depth, they're typically the most important variables. So if you're looking at this graph from top, you'd see most important, and the bottom, not least. These are actually the top variables within our modeling approach. So there's several more, but I just wanted to show the top ones. But with these red arrows, I've identified several of the coherence variables that were quite influential in this machine learning approach. So again, what I'm seeing here with these results is that coherence is again very complementary to SAR backscatter topography for mapping these type of systems. And then with our final kind of general findings that we're seeing the machine learning methods can accurately map these type of hydroecological classes, which is quite important in these areas that where you see quite rapidly changing conditions in these Arctic environments. And also an important aspect of this work is that it was completely SAR based so it wasn't optical based. So you can actually have consistent measurements of how these systems are changing over time in terms of their hydrology and structure. And on the far right image, just to kind of finish off these slides here, are just some examples of some of the output machine learning classifications, followed by some coherence observations, classification, coherence. So some nice visual results there of the study itself. And that is the last study I wanted to showcase. So yeah, thanks everyone for listening today. Hope I was able to showcase some of the wetland mapping, earth observation, machine learning work that I've been working on with Ducks Unlimited and also through my PhD. There's a number of different citations throughout the study that I'm happy to share. The last study that I have up here, that was recently published in Remote Sensing, so titled Mapping Arctic Tundra Hydrogeological Conditions using Sentinel-1A. So happy to share that citation as well. But anyways, that's my last slide. So thanks so much. And thanks, Libby, for letting me present here.
Thank you, Mike. Okay, so we do have some time for questions. I think that people have the ability to unmute themselves if you have a question that you would like to ask, or if you could also put something into the chat, and I believe that that should be able to be readable by everybody. If you are having trouble unmuting, and you can try raising your hand, and then I can find you and unmute you that way. So, does anybody have any questions to start off with? Yes, there's a question in the chat. Mike, do you want to read that out loud for everybody and then just go, because in the recording the chat won't appear, so, and then if you could answer it, that would be great.
Sure. Yep. So the question was the question and statement. So the MCHI decomposition maps show a lot of spatial variability within the classes in the final maps, i.e. detail. Is this information meaningful or useful? Yes, so the spatial variability, I believe so, because it's with the resolution of the RCM data I was working with, so I may have had a bit of an oversight there, but it is very high resolution, five meter SAR data. So my assumption there is that it's capturing some of these very fine spatial detail information within these systems. So even thinking about the permafrost ice wedge networks that have been the focus of that study, what you're getting is kind of a whole network of different characteristics, being the ice wedge itself, the polygonal bogs themselves, which have varying characteristics. So my assumption is that that variability in the scattering contributions is useful, and it's useful information for pattern detection within the deep learning approach. At least is what I'm showing. So one of the interesting things with that work too is looking at the for people knowledgeable of SAR preprocessing, looking at speckle filtering impacts on classification accuracies. So that was kind of some interesting findings relative to that as well. So should we or should we not actually speckle filter when using SAR data of that resolution with deep learning approaches, which kind of have a filtering process with the convolution components in it anyways. And we're actually finding that unfiltered SAR data where you keep a lot of that variable information, like you're kind of pointing out, Mark, is useful for deep learning classification more so than actually a speckle filter approach. So that's kind of an unexpected finding that we were looking at. I didn't actually cover it in my presentation, but happy to talk to you about that after, Mark, if you'd like to connect. That'd be a really interesting finding to talk about. Thanks, Mark. Appreciate it.
Looks like somebody's saying they have to leave early. Okay, there's another detailed question again. If you could read that out, that would be great. Thanks.
Okay, so across the different project, there seems to be a lot of reliance on self-generated training data, whether by field or image interpretation. Has there been any efforts to discuss across different disciplines the meaning of some of those classes? For example, a permafrost scientist or forestry specialist would have a different understanding of upland than what the Canadian wetland classification would be. This has implications to carbon, et cetera as well. Yeah, so thank you for that question. I'll try and tackle it in two different aspects. One of them is the component of needing training data for machine learning, um, also with different components of machine learning. So we have machine learning and we have deep learning. The requirements for actually the amount of training data goes far up when you're doing, for example, deep learning approaches. So there has been some work in different fields of deep learning on how to perhaps automatically generate data for feeding into these networks. One of the next studies that I'm getting into with my PhD, I just haven't got too far into it right now, but it's looking at automatically generating that training data set for a neural network approach, particularly for Arctic surface water mapping. So that's something I've been thinking about too. But again, it is a bit of um, I guess a difficult requirement for some of these approaches. So we show that these machine learning approaches can work well for classifying classes of interest by the expert themselves. But again, how do we kind of get to a more automated approach next, especially for wetlands, which are like the question is getting at here, very can be interpreted quite differently from, say, a permafrost scientist versus a forestry specialist. Um, so at least with some of the work that I've been showcasing here today, I was trying to use very general classes, general thematic classes. So for example, kind of a general permafrost wetland class rather than having the very detailed classes, which can become a bit nuanced and perhaps interpreted differently from different experts. But regardless, it's something that whenever you're doing any of these mapping studies and you're part of the reference data development, you want to ensure that you have someone who's hopefully an expert in that field so that they understand how to define these classes, but how to define them and collect them. But regardless, I think there's always a component of human bias and error within these approaches. Something that again in some of my subsequent projects I'll be looking to address to kind of remove that human bias. But currently, at least in many of these projects, we again do assume some of that bias and error from, regardless that it's an expert opinion. Um, I don't see another question yet, but I will add one more point to that. It actually points to especially the need for field data for in-field data collection. Um, However, we for many of us on this call, I know that we've been working in northern high latitude regions. That field work is very expensive. So often we're trying to look at trying to balance the requirements, the needs, and even just the budgets you're working with for developing training data for mapping purposes. That's always a tough one. Kind of showcase some of the field data that was collected for that Ducks Unlimited project, looking at mapping the Cleacher region. That was a fantastic field campaign where the group of analysts really got to understand the different wetland classes within the region. But yeah, there's quite a need for that in-field knowledge generation. However, again, often trying to balance that the ability to actually get to these regions, which are often remote and expensive.
Thank you very much. Are there any other uh, questions from the audience here? Just another thank you there.
Yeah. Yeah, I'll read that out. Thank you. Indeed, consensus building and CalVal across disciplines will be important for large-scale analysis and uptake of data.
Yeah, one of the things I was thinking about is that, you talked about the application of this wetland mapping to thinking about, waterfowl habitat, but but clearly there are many other sort of areas of interest for which this type of work is important. The was mentioned the carbon, or I'm just wondering if you've been connecting up with other folks who might have interest in this kind of data for different considerations along those lines.
Yeah, great question, Libby. And I'll kind of just briefly introduce some of the work that my organization, Ducks Unlimited Canada, does. So my role is Earth observation wetland map development, but it definitely doesn't end there. So those products go into our organization for feeding many aspects of conservation, whether it's habitat assessments, species predictions, such as the waterfowl modeling that we were showcasing. That's something we've been doing for quite a while as an organization, and we're consistently looking to improve that. But we've seen our products influence a number of different species predictions as well. We've been working on, for example, suitability mapping for bison in Alberta, Canada. So there's a number of different species related pieces that wetland maps go into. Sometimes they're a main covariant in those mapping components. Sometimes they're an additive to several other different thematic maps or temporal data sets, et cetera. But it feeds a lot. And then also, for example, for many, many years, our organization has been working with industry to help improve, for example, transportation across landscapes and boreal systems. So how do we reduce the impacts of road development on wetlands? How do we avoid sensitive wetlands? Have hydrology characteristics maintained, et cetera. So there's a massive influence with different industry partners on how to best operate on the landscape. And then we're seeing, for example, things like with the Clecho project I was talking about, some applications relative to just large-scale land use planning, indigenous protected and conserved areas. So it really kind of the wetland map information in northern regions in particular feeds so many different aspects, especially with our organization like Ducks Unlimited Canada. And it's one reason why you're actually seeing so much dedicated research within the academic field, like my PhD work, to basically improve the efficiency and accuracy of these products over time.
Great. Thank you very much. Um,
Yeah.
oh, there's one more question from Mark in there. If you want to read that out again, that would be great.
Yep. Have you looked at the various Landsat-based map products, AGB, top cover, and their results versus yours? We found some important anomalies over, for example, polygonal ground, mainly owing to the reliance on spectral reflectance measures that reflect non-woody vegetation in troughs. So I haven't looked at these Landsat-based maps yet. I haven't seen their open source availability. We were trying to map shrubs. Um, yeah, so well, in general, that's an interesting point because, again, if we go back to the study that I was showcasing on the polygonal ice wedge network mapping, just to give a bit of a background there, but the majority of the studies that have done mapping of those features has been optically based. Mark here is referencing some Landsat-based products. What I've actually found in the literature as well is some very high-resolution optical-based mapping. And one of the things I was trying to get at with my work is that while the high-res optical data produces very good results, you're then reliant on atmospheric conditions. You don't really have a consistent time series collection of data. Regardless, yeah, I guess the question, oh, agreed, there we go. Yeah, so, great results with optical data. Mark, I would like to look at the Landsat products because, again, I've seen the very high sub 1 meter products. I haven't seen the 30-meter Landsat. Interesting to see what they kind of look like, especially getting at your point in terms of, looking at the spectral reflectance that differs based on woody, non-woody areas, troughs, et cetera. Just for reference, these ice wedge troughs that kind of go through these systems, they can be very, very thin and linear. That you probably have many of them caught within a single Landsat pixel. So I'm interested to see kind of what that reflectance looks like. But again, my study is actually one of the first ones to look at SAR for this application. So we've seen a lot of good results with high-res optical. Let's kind of actually push the field to see if we can have high-res SAR data helping these type of consistent imaging acquisitions. And I'll leave off with one more point there, but I talked about one of the final chapters of my PhD that I haven't been able to get too much yet, but it's on what I'm considering ultra high resolution SAR data for Arctic surface water mapping. It'd be really interesting to look at that data over ice wedge networks, but that data in particular, so I've gained access to some satellite imagery from Capella Space. So it's a sub 1 meter SAR data set. So Mark, it'd be really interesting to look at that type of sub 1 meter SAR data. So something similar to the high res optical data over these networks, and see if you can get a consistent response from the ice wedge, from the polygonal raised areas, etc. But anyways, it is really neat to see where the field of SAR is going, because remote sensing has been so dominated from optical data for so long. But we're seeing a lot of really fascinating platforms of SAR sensors going up. RCM, we're seeing these really high resolution data sets like from Capella Space, and all these other really cool compact pulse sensors going up that I know NASA's taken advantage of. So exciting to see where that field's going with SAR data and all these different applications, especially over Arctic regions.
Okay.
You bet, Mark.
If there are no other questions, we'll wait just a second here. Um, but again, thank you so much, Mike, for agreeing to give this talk. We really appreciate it. It was very interesting, and I'm glad that so many people were able to join us, and look forward to seeing you again. I will be sure to let folks know when we have new talks in the pipeline, and enjoy the rest of your day.
Perfect. Thanks, Libby.